Hello, I am Tinashe Masvaya. Today I want to take you through operating system scheduling algorithms. Scheduling is an important part in multi-programming, multi-processing, usually multi-programming, whereby a processor should determine which process to process at a given time. So CPU scheduling is the basis of multi-programmed operating systems. By switching the CPU among processes, the operating system can make the computer more productive. By scheduling, the operating system will be allocating time to different processes, so that when another process is waiting for the input or for the output, then the processor will be processing another process, so that it will be more efficient than for a processor to lie idle while waiting for input from peripheral devices, which are a bit slower than the microprocessor. A process scheduler schedules different processes to be assigned to the CPU based on particular scheduling algorithms. So there are plenty of scheduling algorithms, which are first come first serve scheduling, shortest job next or shortest job first algorithm, priority scheduling, shortest remaining time, uh, round robin, multi-leveled queuing scheduling. So we are going to go through some of the scheduling algorithms in this lecture. Types of scheduling algorithms. Some of the scheduling algorithms are preemptive and some of them are non-preemptive. Those who are preemptive, it means that the process, or the process which is being processed, can be halted or preempted before it is complete, which means before the process complete, it can be put into a wait state before it completes. And in non-preemptive algorithms, those are algorithms where a process which started to process is not allowed to stop. It should finish its processes, cannot be interrupted or cannot be put into wait state while other other processes can process. So first come first serve algorithm. Jobs are executed on first come first serve basis, so that is clear. And it is a non-preemptive or preemptive scheduling algorithm. That means it can be non-preemptive, first come first serve, or it can be a preemptive first come first serve algorithm. So the operating system determines whether it to use preemptive or non-preemptive. But in other operating systems like Linux, it uses non-preemptive scheduling. It is easy to understand and to implement. Its implementation is based on first in first out queue, and poor in performance, as waiting time is high. So given an example that, well, in this case we have 4 processes. On this table we have process, arrival time, execution time, and service time. Execution is the time which the processor spent on that process. Arrival time is when the time the process arrives at the processor. And process, this is the name of processes. Service time, it means the time at which that process starts to be served. Okay, let's start with P0, process 0. Arrival time is 0, execution time it's 5, and service time it's 0. Why is it 0? Because it arrives at time 0, and at the same time when it arrives, it was then processed at that time. Then P1, arrival time is 1, then execution time is 3, service time is 5. Why is it 5? It is executed when the P0 is finished, then P1 starts to be executed. P2, arrival time is 2, execution time 8. It starts to execute at service time when it's 8. 8, why 8? It's 5 plus 3. So the time will be 8 when process 2, P2 starts to execute. Then process P3 will start to execute after time 16. So on this other table, it's form of a Gantt chart. P0 starts to execute up to T5. Then P1 starts to execute from T5 to let me go back. From T5 to T8. Then P2 starts from T8 to T16. Then P3 starts from T16 to T22. So the total time spent is 22 T. Then let's go to the average wait time and wait time. For P1, the wait time is 0 minus 0, because it starts to be executed at 0. It arrives at 0 and starts to be executed at 0. So we say 0 minus 0 will then get 0. P2, we say 5 minus 1. It starts to execute at T5 and it arrives at T1. So we say 5 service time minus arrival time. That's the wait time. On P2 it's 8 minus 2, which is 6. So P3, 16 minus 3, it arrives at T3. So 16 minus 3 we get 13. So we add the total wait time and divide by the number of processes, which is 4, then we get 5.75, which is the average wait time, using the first in, first come, first serve algorithm. We then go to shortest job next. This is also known as shortest job first. This is a non-preemptive or a preemptive scheduling algorithm. It can be a non-preemptive or a preemptive algorithm. Best approach to minimize wait time is to implement in batch processing, where required CPU time is known in advance. Impossible to implement in interactive systems where required CPU time is not known. In interactive systems, so you cannot determine the CPU time, because it will be determined by the processes which are interacting. You don't know how long will they take to finish their processes. The processor should know in advance how much time process will take. Okay, so in this case we are using now shortest job next. So we have all the 4 processes. On the execution time, we know that P1 is the shortest CPU time. So on processing, we start to process P1. So the safe time will be 0. Then the other shortest job is 5. So 5 will start to execute at T3, safe time when it's 3. After that, the next in the hierarchy is 6. Is the shortest again between 6 and 8. So 6 will execute at time safe time 8, and then finally 8 will execute at safe time 16. So the total time is 22. So let's calculate the waiting time. P3, sorry, P1 does not wait, so the wait time is 0. P0 wait 3, T3, so 3 minus 0 we get 0 is the arrival time, we get 3. 16 minus 2 we get 14. 8 minus 3, which is the arrival time, we get 5. So we add the total and divide by 4, we get the 5.50 as the average wait time. Then priority-based scheduling. Priority-based scheduling is a non-preemptive algorithm, and one of the most common scheduling algorithm in batch systems. Each process is assigned a priority. Process with highest priority is to be executed first, and so on. Processes with same priority are executed on the first come first served basis. Priorities can be decided based on memory requirements, time requirements, or any other resource requirement. So on our 4 processes, in this case we now have the another column for the priority. We have priority 1, priority 2, and priority 1 and priority 3. So it means P3 is the highest priority, so it should execute first. So P3 will execute first. The other process with highest priority is 2. The second in that hierarchy is 2. Then so second 2 we start to execute after safe time 6, because the execution time of P3 is 6. Then it executes for T3, so 3 plus 6 it becomes 9. So in this time first come first served basis, P0 arrive first, then P2 arrives later, so P0 will be executed first after 9 safe time is when it's 9. Then lastly P2 will be executed at safe time 14. Total is 22. Let's see the waiting time. P0 wait 9 minus 0, which is the arrival time, which is 9. P1 6 minus 1 5. P2 wait for 14 minus 2 12. P3 will not wait, so average divided by 4, and we get the average. Okay, shortest remaining time. Shortest remaining time is the preemptive version of the shortest job next. So it's just like the shortest job next, but this one is the it will be preemptive. The job which is in or the process which is in execution can be preempted or can be put at a wait state, while another job with the shortest time is executed. The processor is allocated to the job closest to uh, completion, but it can be preempted by a newer ready job with shorter time to complete. Impossible to implement in interactive systems where required CPU time is not known. It is also it is often used in batch environment where shortest jobs need to be to give when shortest jobs need to give preference. And round robin scheduling. Round robin is the preemptive process scheduling algorithm. Each process is provided a fixed time to execute, and that fixed time is called a quantum. Once a process is executed for a given time period, it is preempted and other process execute for a given time period. Context switching is used to save states of preempted processes. The major challenge with round robin scheduling is when processes depend on the outcome of another processes. The processor can process, and before the input is processed, the other processes will start to be at a wait state, which might affect the whole process. Okay, with our four processes, let's look at the quantum. Let's remove. Okay, let's ignore this part for the safest time. Let's ignore this part of the safest time, and let's just look on these three columns. So process we have 3, so process 5 will execute for 3t or 3 seconds. Then process 1 also execute for 3 seconds. When process 1 execute for 3 seconds, it means it finishes its processes. Then P2 execute for 3, it's 3 seconds, and P3 execute for 3 seconds, and P0 will be allocated its time, but P0 is already executed for 3 seconds, so it has 2 seconds remaining, so it will finish its 2 seconds. Then P2 has 5 seconds remaining, so it will execute its 3 seconds. Then P3, it will execute its 3 seconds and finishes. Then lastly, P2 will finish its 2 seconds remaining. For the average wait time, P0 it starts to execute its 3 seconds and wait for 12 seconds. So we multiply, we subtract by 3 and we get 9. Then for T1 it will wait for the first 3 seconds, then it will execute. So 3 minus 1 we get 2. For P2 it executed 3 stages. First stage 6 minus 2. First stage 6 minus 2 we get 4. Then the next stage it wait for 5, and the next stage for 3. Then the total 20, sorry, the total 12. P3 it wait for 9 for the first time minus 3. The second time it will wait for 17 minus 12. Then it becomes 11. So the average wait time will be 24. So in this case, for let's just do P1. P1 is 0 minus 0. Then the next was 12 minus 3. Why 12 minus 3? It goes to the wait state at T3, then start execute at T12. So T3 will act as if is the arrival time, just like T process 2 P2. When it execute up to 9, then when it start to execute at 14, we say 14 minus 9. Then when it starts to execute at 20, we say 20 minus 17. So in this case 17 was acting as if it's the arrival time. So thus the scheduling algorithms in the operating system. Lecture is ended. Thank you. God bless you.